Hello and welcome back. This is the second lecture in Chapter 2. Previously, we studied how to analyze the motion of objects that had uniform motion, meaning that they had a constant velocity. They moved in one direction without speeding up, slowing down, or changing direction. We're still going to stick with one-dimensional motion, but we're going to add in the idea of changing speeds. So what happens if something speeds up or slows down? How do we deal with that? How do we represent that? And how do we deal with that mathematically? And that's what we're going to look at today. So even though a constant velocity model is really important, it's rare in the real world for things to travel very long with a totally constant velocity. And even if you want to switch between two relatively constant velocities, there's some period of time where you have to speed up or slow down to achieve that. So much more common in the real world is to have a velocity that changes with time. For example, if you look at your car as you're driving down the road, at any instant of time, your speedometer is going to tell you how fast you're going at that instant. But that's not going to generally stay the same for very long, unless maybe you've got the cruise control set. And even then it varies a little bit as you go up and down hills or so on. That number tells you what's known as the instantaneous velocity. That's the velocity at a very certain instant in time. Now that may or may not be equal to the average velocity. In cases where you do have uniform motion, the velocity is the same at every moment in time. It's not changing over time. So the velocity at any moment is equal to the average. That's not true once you have motion that does speed up or slow down. So in that case, if we wanted to find the instantaneous velocity at a certain point, what we can imagine doing is to find the average over smaller and smaller and smaller time intervals. So if we find the average velocity over a second, that's going to give you a pretty good approximation of how fast you're moving at that moment, because the second is a really short period of time. If we find average velocity over a much longer period of time, it's not going to give you a good estimate of the instantaneous velocity. So if we take the limit as that time interval gets closer and closer and closer to zero, remembering that our definition of velocity is that it is the change in position over the change in time, the limit as delta t goes to zero becomes the derivative of position with respect to time. So if we have a function for the velocity or the position, we can differentiate that position function to get the velocity function, and then we can know exactly what the velocity is at any point in time. And we're going to come back and do that a little bit later in this course. Let's look at what this looks like on some different types of graphs. So if we have a position versus time graph for an object that is accelerating. Accelerating means it's changing its speed. It might look something like this. Notice that the position time graph is curved. Anytime you see a curved line on a position time graph, you should immediately think that this is an object that is either speeding up or slowing down. A straight line indicates uniform motion. But what if we were to zoom in on one tiny little point right here, and we blew that up and looked at just the time right around that time point? We would see that if we zoomed really close in, it would look almost like a straight line, and we could find the average over a very small time interval. That would give us a good approximation of the slope, therefore of the velocity at that exact moment. What would give us an even better approximation is if we could find the slope of the tangent line to the curve. And as you all know, the slope of the tangent line is the same thing as finding the derivative if we have a function. So if we have a graph, we can draw a tangent line like this, a tangent line being a line that only touches the graph at one single point. We could find that graph, find the slope of that graph to give us what the velocity is. If we have an equation, we can also differentiate that in order to find what the velocity is at any point along the motion. So once again, just summarizing what we've been talking about here for the past few slides. As delta t continues to get smaller, the average velocity gets closer and closer and closer to the instantaneous velocity. As it approaches zero, this turns into a derivative. So the slope of the position time graph at any given point in time is still equal to the velocity. And that now we can see that that is also equal to the derivative of a position function at a certain point in time. So, quick question. Let's review what we've been talking about. This is probably the easiest question we'll have all year. The slope at a point on a position versus time graph is what? We've said this no less than 100 times. So I hope that everybody can tell by now that the slope is equal to the velocity. And that is true whether you have a constant velocity, where you're just going to have one constant slope, or whether you have a changing velocity, where you have a curved line on a position time graph, and you may have multiple different slopes that change as the motion proceeds. The slope at any one point is going to tell you what the velocity is. So let's look at an example here. This is a position versus time graph of an elevator. We want to try to figure out at which point does the elevator have the smallest velocity, and at which point does it have the biggest velocity, and what does its velocity versus time graph actually look like. So let's try to answer that first question. At which point on this graph does the elevator have the smallest velocity? Well, I think it's pretty clear that we can see that the slope here at point C is actually 0. If we were to draw a tangent line there, it's just continuing at 0. So the velocity here is equal to 0. That's as small as it gets. There's another point, however, at which it also has 0 velocity, which you might not notice right away, and that's point A. Point A is not a flat line like C, but if we draw the tangent line there, it's very obvious that A also has a velocity of 0 at that point. So at which point does the elevator have the least velocity? A and C. At both of those, the velocity equals 0. At which point does it have the biggest velocity? Well, that's going to be right here. If we draw a tangent line there, we see that that is the steepest velocity that we're going to have. It is less steep before you get to B, and it becomes less steep again after you leave B and go towards C. So now let's try to turn that into a velocity time graph. What would that look like? Well, initially, we want to break this up into segments. Initially, from here to here, we have a negative velocity. And is that velocity getting bigger or smaller? Well, it's getting closer to 0. It starts out with a fairly large negative velocity and it goes to 0. So we're going to start out our velocity down here. And we're going to go to 0. And that's going to be point A. Now as we go on, our velocity gets bigger and bigger and bigger and bigger to B, and then it starts to slow down again as it goes towards C. So we're going to have an increasing positive velocity all the way up to point B, and then a decreasing positive velocity all the way to point C, and then or to right before point C, anywhere C would be kind of right in here. Then you have 0 velocity after that. So once again, the shape of this velocity graph does not necessarily correspond to exactly what the position graph looks like, but it shows you what the slope is at any point. Let's look at a few other questions to see if you can work on taking the motion diagram and turning it into position time, velocity time graphs. Some of these will be uniform motion and some of them will be changing velocities. So let's look at this first one. Which position time graph is going to match this motion diagram? Notice here that we have two segments of the motion. Here we have a small velocity and here we have a large velocity, a relatively larger velocity anyway. What is that going to look like on the position time graph? Well, initially you're going to have a less steep slope that's going to be followed by a more steep slope. You also need to notice where the 0 point is. So initially it starts with a negative position and it moves to a positive position. So the position time graph that matches that is actually E. Look at another, the same motion diagram, but which velocity time graph matches that? Well, again, even though we have a negative position here in the beginning, we still have a positive velocity, and that velocity gets bigger over time. And so the correct graph would be C. Now what happens if that same car turns around and goes back the other direction? Well, we start with a negative velocity, a small negative velocity, and it turns into a bigger negative velocity. So that would give us the velocity time graph that looks like D. So once again, just to revisit this, we're going to hit this idea several times so everyone remembers it. The velocity is the slope of the position time graph, which is equal to the derivative. We will get to doing problems just a little bit later where we actually have a function here, and then we will be able to solve for the velocity when we have a function of position. So let's look at an example of how we would do that. Suppose the position of a particle as a function of time is 2t squared, where t is in seconds. So this is something that's going to be a curved graph, right? It's a part of a parabola. And we can see here, if we draw that on a graph, 2t squared would look something like this. It's a curved graph. And we want to find what is the particle's velocity at any point in time, all right? So if we want to know it at any point in time, what we need to do is we need to take this equation that we have for the function of position, and we need to find what the velocity function is. And we do that by finding the derivative of the position with respect to time. And that gives us that the derivative of 2t squared is equal to 4t. Now that means that now we have a function for velocity, so we can plug in a time and then we can know what the velocity is at that time. So if we wanted to, for example, know what the velocity was at 3 seconds, we could plug in velocity at 3 seconds is equal to 4 times 3, which is meters, 12 meters per second. That's going to tell you what the velocity actually is here, and that's also going to tell you what the slope of this line is. So, let's look at a couple more examples. Here's a position graph of an object. At t equals 1.5 seconds, what is the object's velocity? Well, this is a case where we are not specifically given an equation. So what do we need to do if we're not given an equation? We need to just find the slope directly. 1.5 seconds is right here. So when it's asking you for the speed at that point, you need to know what is the slope of this line. Right? So to find the slope of that line, we would say it's 20 meters minus 0 divided by 2 seconds minus 1 second, which gives you 20 meters per second. Now what would be the velocity at 3 seconds? So at 3 seconds we need to find the slope of this line. So finding the slope of that line would be 0 meters minus 20 divided by 4 meters minus 2 meters. So we would have minus 20 meters over 2 seconds. Excuse me, these should be seconds, so let me fix that. 4 seconds minus 2 seconds. So 20 meters over 2 seconds gives you minus 10 meters per second. Now we could tell some things about this before we even calculated anything, because we can see that it should be negative. It's a negative slope. We can also tell that the magnitude of that should be smaller than the previous one because it's not as steep of a slope. So this would be minus 10 meters per second. Next question. This is a tricky one. When do objects 1 and 2 have the same velocity? This is a position time graph, notice. So a position time graph does not tell you what the velocity is directly. Everybody knows, how do we find the velocity from a position time graph, right? The slope. So when it asks where they have the same velocity, what it's really asking is where do they have the same slope? So when most people look at this question, it's tempting to say here at t0, right? Because that's where it looks like the lines intersect. But what is that really telling you? This is telling you that that is the point at which they have the same position. Does it mean that they have the same velocity just because they have the same position? No, of course not. As an example of that, imagine if you were in your car and you tried to pass another car. Well, at the moment you pass that car, both cars could be said to have the same position. You're side by side. But you don't have the same velocity. You are clearly going faster than the other car because you're passing it. So they don't have to be at the same velocity just because they're at the same position. What we would want to notice is that somewhere, maybe about right here, if we were to draw a tangent line at that point, then this line is roughly parallel to this line. And so at that point, they would have the same velocity because the slope would be the same. And that would be at some point before t0. We don't know exactly where. We don't have any other numbers on the graph, but we know it's somewhere before then. Okay, so now let's look at how we can find the position from the velocity. We have already looked at how to find the velocity if we know the position, either on a graph by finding the slope or mathematically by finding the derivative of a function. But what if it's the other way around? What if we know the velocity either as a graph or as a function, and we want to know what the position is? Well, velocity can't really tell us everything about position. We need to know the initial starting position outside of the velocity. But then once we have the starting position, what the velocity can tell us is it can tell us the displacement. It can tell us how much did the velocity change. So we can say that the final position of an object is equal to the initial position of the object plus the integral of the velocity function between those two time points. So that tells you how much the position actually changed. So this part right here is equal to the displacement, which we say delta S. So if we have an equation for the velocity, we can integrate that and find out get an equation then for the position function. And then we could use that to find the position at any point. What about if we just had a graph of the velocity? Well, we could do that too, because what is an actual integral? An integral is equal to the area under a graph. We already did that for very simple uniform motion problems, but we can also do it for more complicated motion problems. Let's look at what that would be like. So imagine that you have a velocity time graph that looks something like this. It's not a straight line. What we can imagine doing is breaking this up into these individual rectangles, right? We can find the area of each of these and add them together to get the total area under the curve, which gives you the displacement. Now, once again, we can do this graphically. We can also do this by finding the integral. In fact, those are the same thing. When you find an integral, what you are literally doing is finding the area under the curve. So let's look at an example of that. Here's a velocity graph of an object at the origin. At 4 seconds, what is the object's position? So assume that it starts at x equals 0. So again, we have to know the initial starting point to figure out the final position. This tells you how much the position changes. So here, we don't have an equation. We could try to write an equation and then integrate it, but that's more complicated than we really need to make it. All we need to do here is we need to find this area. So we can break this up into two areas, a rectangle and a triangle. The area of the first one, it's a rectangle. So the area is simply the height of the rectangle times the width of the rectangle, which gives you 8 meters. For the second one, it's a triangle. The area of a triangle is 1/2 the base of the triangle times the height, which is 4 meters per second. That gives you 4 meters. And one thing I'll point out here, the base of this second triangle is just 2. It's tempting to write 4 because you see that it ends at 4, but remember it started at 2. So when we're talking about the base of the triangle, we're talking about this length right here, which is 4 minus 2, or simply 2 seconds. So what is the total displacement? The sum of both of these together, which is 12 meters. And since it started at 0, the final position then would be equal to exactly 12 meters. Let's look at another example of that. What if in this case we had an equation? We know that the velocity is 4 times t. How far does this race car move in the first 3 seconds? All right. So what we really need to do is, once again, integrate this by finding the area under the curve. So we can look at that. We can figure out by just using the formula for the area of a triangle, because this is a triangular shape. So the area of a triangle is simply 1/2 the base times the height. We can use the function to figure out what it is at 3 seconds, right? So what is the velocity at 3 seconds? Equal to 4 times 3, which is 12. So that's the height. The width of this is 3. So 1/2 12 times 3 equals 18. So we know from this that the race car moves 18 meters during the first 3 seconds of its motion.